All right, last time well, the last couple of times we've been talking about this discovery of electrons. And last time we covered this very clever experiment that Robert Millikan did, where he sprayed out this fine mist of little oil drops and had them drop between two electrically charged plates. And I described how by varying the voltage between the plates, he could get these little tiny drops of oil that had electric charges on them to balance between the plates, because the gravity's pulling them down and the electrical force he had arranged to be pushing them up. And if he balanced those forces, then he could set the electrical force equal to the gravitational force. And what came out of that was a calculation for what the electric charge was of these little tiny oil drops. Because if the charge was big, obviously, then the electrical force would be too big and they would go up. If they weren't charged at all, of course, they would just fall down due to gravity. But some of them were about the right charge, and he could actually adjust his voltage to get them to hover between the plates. Now, what he found in every case where he was able to calculate the electric charge on one of these little oil drops, what he found was that, so this is Millikan's oil drop experiment. And the result that we got at the very end last time was that he calculated that the electric charge on a drop always came out equal to some integer, let's say n, multiplied by this very small number, 10 to the negative 19th coulombs, so 1.6 times 10 to the negative 19th coulombs. Now, coulomb is just a unit of electric charge. It's if you let 1 amp go through a circuit for 1 second, the total amount of charge going through the wire is defined as 1 coulomb. So this is 1.6, in fact, divided by 1 with 19 zeros after it, right? I mean, that's a little tiny number. Okay, now, since the charge on every single one of these oil drops was always some integer multiplied by this charge, then, if we're thinking in terms of particles, obviously, this has to be the charge on one of these charged particles that is on the oil drops. And so that is the charge on the electron, which is what Millikan was after. Now, we can put this number together. So this implies that charge on single electron equals this 1.6 times 10 to the negative 19th coulombs. Switch to green here. Now we can put this number together with the number that we got a couple of weeks ago when Thomson calculated, remember, the charge to mass ratio of the electron, right? I left it as a exercise for you to work out the mass of the electron at the end of last class. Did anybody do that? Sure. Oh, okay. But you did it. That's what counts. All right, we'll do it again. Remember that so from Thomson's experiment, we had this result, that the Q over M for an electron is equal to 1.76 times 10 to the 11th coulombs per kilogram. Well, if you, this is the Q now. So I mean, this is all Thomson could do with his experiment, is the charge per mass. But now we've got the charge, so we can figure out the mass. I mean, all you have to do is divide this little tiny number by this big number, and you get the mass. So that implies the mass of an electron is, let me see, it comes to 9.1 times 10 to the minus 31 kilograms. This is an unimaginably small number. I mean, you can see how these scientists, by actually observing things like deflections of beams in magnetic fields and hovering oil drops, can come up with experimental data that allows them to calculate this number. But this number itself, I mean, try to imagine how small this is. I mean, it's easy for us to imagine a kilogram. A kilogram is 2.2 pounds. I mean, you can hold that in your hand, and feel the weight of it. But, you know, that would be, I mean, how many electrons? That would be 10 to the 30th electrons would weigh that much. So, I mean, a book like this, let's say this book is a kilogram, probably is about that. Well, I mean, if we had this same weight of electrons, we would have to have 10 to the 30th electrons. 1 with 30 zeros after it. That's a lot of electrons. Okay. Now, what? Now, once we have this number, we know how much an electron weighs now. We can actually figure out something else that no one had an accurate estimate of before. We can figure out how many, I mean, I've been telling you about atomic weights now for months, okay? And you know that that 1 gram of hydrogen has the same number of atoms as 16 grams of oxygen, right? So we know these relative weights of the different atoms. But one thing that scientists never knew is how many atoms there are in 1 gram of hydrogen or 16 grams of oxygen. Okay, they never they never were able to get that, at least not accurately. Well, now there's a way to do that using these numbers that were figured out at the beginning of the 20th century. And so let me go back now and fill in that missing piece of the puzzle. And the way that scientists were able to do that is to, after they got these results, to go back and look at Faraday's results in his electrolysis experiment. Okay, so let's. Yes? No, he knew the same number of atoms were in equal volumes of gases contained. That's what I'm going to calculate right now. Avogadro never knew Avogadro's number.
Oh, he didn't. Okay.
Which seems paradoxical, but he would have had information that just didn't exist back in his day. So Avogadro came up with his law that said, well, if you have equal volumes of gases, they have to contain equal numbers of molecules. But as far as what that number was, he didn't know. But now we can figure it out. So revisit Faraday's electrolysis experiments. Okay, now let me give you a typical result from Faraday's experiment. He didn't do exactly this, but he could have. Let's say that we have a big vat of salt water. Okay, so now we put in a big electrode here. Hook it up to a big battery. And we're going to make, let's say we make this the positive electrode and this the negative over here. And what's going to happen here? First, what is salt? Does anybody remember? Daniel. Sodium chloride. So we have sodium chloride in here. Now, what happens when I turn on my battery here? Daniel.
Sodium should go to the positive and chlorine to the negative because we know that chlorine is negative. It is actually it's positive and it will attract to the negative.
Well, no, you had it right. You said chlorine was negative, and that part's right. So what happens here, salt easily splits up into what Faraday called ions, right? And what happens is you have, when it splits up like this, with the chlorine negatively charged and the sodium positively charged. Troy.
Doesn't the water also split?
Oh, well, in this case, it's so much easier to split the sodium and the chlorine that they'll split up so much easier than a water molecule will, that basically all the current is carried by the sodium and the chlorine. So the what you'll have going on here is you'll see chlorine gas bubbling up. I mean, that this negative chlorine atoms will go to this positive electrode, and the positive sodium atoms will go to the negative electrode. So you'll see chlorine gas bubbling up at this electrode, and you'll see sodium is a metal. Okay, so it actually just collects on this negative plate. Now, let's say that we just leave this going for a day, and we measure the current that is going that whole time. And let's say that we, in our system here, we have a current that I've picked this number deliberately in order to make another number come out the way I want it to later. Let's say that we have a current of 1.12 amps. Okay? And we let it go with that current for an entire day. Start it going at 9 o'clock in the morning, come back 9 o'clock in the morning the next day. Now, what we disconnect the battery. We pull this negative electrode out, and we measure how much sodium has accumulated on that electrode. Just weigh it. Okay, so mass of sodium turns out to equal 23 grams. Now, not entirely coincidentally, 23 happens to be the atomic weight of sodium. That's why I picked this current the way I did and let it go for a day. So the number of sodium atoms that have carried, electricity to this electrode, there's a number of sodium atoms that have reacted here, is exactly the same number of atoms that we have in 1 gram of hydrogen or 16 grams of oxygen, right? Because this is the atomic weight of sodium. 23 grams of sodium has the same number of atoms as 1 gram of hydrogen or 16 grams of oxygen or 12 grams of carbon. So if we can figure out the number of atoms that are contained in 23 grams of sodium, we know the number of atoms in 1 gram of hydrogen, which is what we defined as a mole before, if you remember that unit. Okay, we didn't know what number of atoms were in a mole, but we defined the number of atoms in 1 gram of hydrogen as a mole. Okay, so now we can. Does anybody see how we can figure out the number of atoms here? No. Evan?
Because if the current, a constant amount of current always has the same number of atoms that are affected by the amount of current.
Yeah.
So you could use that with, I forgot.
Well, do we know the total amount of charge that has gone through this circuit? Yeah, we do, right? Because we know the current and we know how long it's been going on. Okay, so first let's just figure out that. So let's get total charge. That has to equal the current multiplied by the time, right? So it's this 1.12 amps. Now, we need to use consistent units here, right? We can't just write 1 for days. We need seconds, right? If we want this in coulombs, because coulombs that unit is consistent with amps and seconds, not amps and days. So we need the number of seconds. So how many seconds in a day? Well, you can work that out. It's 60 times 60 times 24, right? So, well, let's just write that down. 60 times 60 times 24 seconds. And if you work out those numbers, what did I get? I think it comes out to 86,400. And that comes out to a whopping big number of coulombs. Okay. 96,500 coulombs. That's a lot of coulombs. All right, so that, now, if we knew the charge on one of these sodium atoms, then we would know how many atoms it takes to come up with that much charge, right? Do we know the charge on a sodium atom? How would you expect that to be related to the charge on an electron? You're guessing the same. Yeah, it turns out that's a really good guess, because, and here's why it's a good guess. We know that there are some atoms, Faraday actually figured out that there are some atoms that are doubly charged. Like he determined, I think I told you about lead and copper actually have twice the amount of charge per atom as sodium does. Well, so when atoms get charged as ions, they get singly charged or they get doubly charged, or like in the case of aluminum, they get triply charged. Okay, but it's a single, double, or triple charge. It's nothing in between. Well, the natural thing to do here, of course, is to interpret that as in terms of the electrons. We've discovered that there are these little tiny particles that are in atoms, and they're charged particles. So what has happened when this salt molecule breaks up? Okay, and each part, the chlorine becomes singly negatively charged, and the sodium becomes single positive charge. What has physically happened in the breaking of this salt molecule? Can you see, Troy?
Some amount of electrons have become.
The chlorine has stolen an electron from the sodium. Okay, I mean, that, of course, if you interpret it that way, that explains why these atoms, when they break into these charged particles, are always like singly charged or doubly charged. I mean, when you have something like Faraday discovered when you have something like lead sulfate, that it breaks into doubly charged atoms. So the lead will become doubly charged, and then the rest of this, the sulfate ion will become doubly charged. Well, there, the sulfur oxide part of this has just stolen 2 electrons from the lead. You can only steal integer numbers of electrons, right? Because they only come in integer numbers. So that is exactly what was happening in these electrons. Now, Faraday didn't know anything about electrons, but if he had, he would have seen, oh, that must be what's going on here, that chlorine steals an electron from the sodium. So what that means is that the charge on this sodium atom is exactly the same as the charge on the electron. Same in magnitude and just opposite sign, right? Because it was neutral, and then you took this negative particle away from it, leaving it positively charged by the exact amount of that negative charge that you removed. Okay? So how do we figure out how many sodium atoms in 23 grams of sodium now? Well, there's the total amount of charge in this amount of sodium. Evan, what's the charge? Well, let me just write this down. This is your final clue. Okay, charge on sodium equals charge on electron, and that is this little tiny number that we had before, right? Yeah.
We take the total amount of charge and divide it by the charge of 1 electron.
Yep. That's going to give it to you. That's going to tell you exactly the number of sodium atoms in this 23 grams. Yeah, Troy.
Won't that just tell you the number of electrons?
Yeah, that'll tell you exactly. That will tell you the number of electrons that this sodium grabbed from this negative plate. But that's going to be exactly equal to the number of sodium atoms because the plate is neutral. See, each one of these sodiums is missing 1 electron. It's going to take 1 electron in order to get neutral again. Okay, so the number of electrons is equal to the number of sodium atoms. Well, so let's just, you can see this is going to be a big number, right? We've already got, pretty big number here, almost 100,000. We're dividing it by a little tiny number. So here's what we get. Number of sodium atoms in 23 grams equals 6 times 10 to the 23rd. 6 followed by 23 zeros. Now that is the number of atoms in 23 grams of sodium. Now a gram, I think a penny weighs about a gram. Okay, so if you have a roll of pennies, that would be 50 grams of copper, right? When they used to be made out of copper, and let me see. The atomic weight of copper is 64. Yeah, that would be almost this number of, I mean, a little less than this number of atoms. 6 times 10 to the 23rd. It's a huge number. Yeah.
How did they find that when sodium chloride splits, it's always single? It's always a single.
Oh, actually, I mean, when Faraday first did this experiment, he wouldn't have known that. But what he did notice was the amount of electricity was directly related to the amount of mass that, or the atomic weight that accumulated on one of the plates. Okay. Now, then he noticed that 23 grams of sodium would generate which is, a full atomic weight of sodium, would generate exactly the same amount of electricity as half of an atomic weight of lead, say. So, I mean, that he can directly measure. Okay. And so he noticed that there was this relationship between the electricity generated and the atomic weight of material. But some materials, it took a full atomic weight to generate that amount of electricity. Some it only took half of an atomic weight. Some it took exactly a third of the atomic weight to generate that same amount of electricity. And of course, this is directly related to the concept of valence that we talked about. So anyway, sodium has a valence of 1, and it takes a full atomic weight of sodium to generate this amount of electricity, the 96,000 coulombs that we talked about. So that means that the sodium atom has to be singly charged. Okay, now I know I've been throwing a lot of numbers around on the board this morning, but I think, after all the time we spent talking about atoms this year, it's nice to, get a real feel for how unimaginably small these little atoms are, and how many there are. Like I say, a roll of pennies contains almost this, over 10 to the 23rd atoms. That's just okay. Notice scientists waited a long time to get an accurate determination of this number, because Avogadro came up with his idea almost 100 years earlier, and but they had to come to an understanding of electrons, before they could get an accurate determination of the number of atoms in one atomic weight. Okay, now I thought it would be fun to go back and remember that one of the key experiments, key events in the history of electricity that started this subject going and convinced people that electricity was a powerful force in nature was, well, what was the first experiment that really convinced people how powerful electricity was? You know, it wasn't when they rubbed little pieces of amber and saw that they could attract little tiny bits of straw. I mean, that's not too impressive, right? Ben.
The glass ball generator.
The what?
The glass ball generator.
Oh, I was actually thinking of something after that. Sure.
When Franklin showed that lightning was alive.
Yeah, when lightning was electricity. I mean, that's when people could see, Jesus, this stuff isn't just, creating little sparks in a lab. This can split oak trees and knock down houses. So that made people realize how powerful electricity could be, and opened the way toward the whole electrical age that we live in now. Let's look back at lightning now from the perspective of all the knowledge scientists have today. There were lots of things about lightning that Franklin didn't know. Well, can you think of questions you might have about lightning that Franklin couldn't have answered? Sure.
What's the charge?
Yeah, he had no idea. Franklin wouldn't have had any clue. He didn't even know how to measure electric charge. He didn't really know anything about electric currents. The battery hadn't even been discovered yet. Now, Franklin did realize that that these thunderclouds had to be charged up electrically in order to get this discharge, this huge spark that we call lightning. But did he even know what charge they were? Okay, he didn't even know which direction the current was going. So there's a lot about lightning that Franklin didn't know. But since then we figured it out, and we can use this idea of ions and electrons to understand what's going on in a thunderstorm. So it turns out that, remember when 400 years ago, a scientist named Gilbert discovered that the Earth was a giant magnet, right? Well, what scientists came to realize about when they studied atmospheric electricity and lightning was that the Earth is not only a giant magnet, it's a giant battery. The Earth is an electric battery. Okay, so I want to tell you a little bit about how this huge battery works. Let's start. Let me see. Let's just call this atmospheric electricity and lightning. Yeah. Now, it turns out that the Earth is negatively charged. If you take let's say, let's just write that point down. Surface of Earth is negatively charged. Okay, so there's the surface of the Earth. Now, if you take a metal plate, and just a flat metal plate, and you ground it, hook it to the ground, it will have negative charges on it. And you can actually measure those negative charges by if you take another plate now and put it over the first plate, the charges will run off the lower plate onto the top plate. And you can measure that current and actually get an estimate for exactly how negatively charged the Earth is. So scientists have done this and proven, yes, the Earth has a significant negative charge on it. Now, let me see. Now, it turns out that there are positive charges high up in the atmosphere. And, some of them come from space. There's things called cosmic rays. And so way up in the atmosphere, you have positive charges. Now, what would you expect to happen if the Earth is negatively charged and there's these positive charges high up in the atmosphere? What's going to happen? Troy?
Electricity's gonna go.
Yeah, there's going to be an attraction, right? So these positive charges are going to start coming down. And in fact, that happens. If you look at the Earth as a whole, there is scientists have estimated that the total current flowing from the atmosphere down to the Earth's surface, so total current flowing from atmosphere down to ground is in amps. Any guesses? No, that's too hard a question. 1,800 amps. That's a big current. Sure.
Is that every second or every minute or every hour?
Oh, well, amps is coulombs per second. Okay, so that's right. There would be 1,800 coulombs of charge coming down every second. Now, one thing you might wonder about is, isn't this, we're out of time for this morning, I guess. But one thing to think about here is, why does this keep going on? Why doesn't this current just discharge the Earth? I'll pick that up this afternoon and explain why.